In this section, we move from Fabric architecture to production operations. You'll see how peers, orderers, and CAs map to Kubernetes primitives and how that foundation supports secure, scalable enterprise deployments. You already have the Fabric foundation: architecture, transactions, privacy, chain code, access control, and deployment patterns. Now we'll turn that knowledge into operations by running Fabric components on Kubernetes, then hardening, scaling, monitoring, and recovering them. Hyperledger Fabric fits naturally into a container model. Peers, orderers, certificate authorities, CouchDB, and chaincode services can each run as managed pods. Around those containers, Kubernetes provides scheduling, health checks, service discovery, and safer rollout patterns. The enterprise value is consistency. The same manifests, Helm charts, operators, and GitOps pipelines can move from development toward production. But Kubernetes is not magic. It shifts complexity into platform design, security, networking, and governance. Each Fabric component needs the right Kubernetes primitive behind it. Peers and orderers run as pods, often managed by deployments or StatefulSets when stable identity and storage matter. Services expose them, ingress can route external traffic, and network policies limit who can connect. Config maps hold non-sensitive settings. Secrets protect certificates and keys, and persistent volumes preserve ledgers. Fabric CA manages identities, while CouchDB supports rich state queries beside peers. Peers and orderers may look similar as Kubernetes workloads, but they have different operational needs. Peers must keep ledger data, private data, indexes, and state database content attached to the right identity. Orderers need stable TLS identity, reachable endpoints, and carefully controlled consensus membership changes. StatefulSets are often preferred when identity and storage must survive restarts. Deployments can work for simpler, more replaceable patterns. Add probes, resource requests, and anti-affinity so failures recover predictably. Beyond peer and ordering nodes, Fabric relies on supporting services that need the same operational discipline. The CA is especially sensitive because it creates the certificates that define every identity. CouchDB enables rich state queries, but it also needs persistence, authentication, sizing, and backups. Chaincode as a service separates execution from the peer, allowing it to be deployed and scaled independently. The key is consistent configuration across peers, services, and connection profiles, or transactions will fail. Fabric state has to survive pod restarts, node failures, and planned maintenance. Peer ledgers, private data, CouchDB state, and orderer data belong on persistent volume claims, not container disks. The storage class matters because it controls latency, replication, zone behavior, and restore options. Backups must cover more than blocks, including crypto material, channel artifacts, and configuration. Kubernetes can reschedule workloads, but Fabric recovery only works when identity, ledger state, and database consistency come back together. Networking comes down to choosing the right endpoint for each traffic path. Inside one Kubernetes cluster, cluster IP services usually handle peer gossip, chain code, CA, and orderer communication without exposing pods directly. For clients or partner organizations outside the cluster, you may introduce load balancers, node ports, or ingress depending on security and routing needs. The critical detail is consistency. The DNS names clients use must match TLS certificate SANs, or Fabric connections will fail during the handshake. Namespaces provide the first boundary around operational responsibility. In Fabric, that usually means separating organizations, environments, or both, so peers, CAs, CouchDB, and secrets are managed in the right scope. RBAC then turns those boundaries into permissions. Platform teams get broad control, organization admins get their domain, and automation gets only what it needs. Predictable, version-controlled names also make deployment automation, audits, and governance much easier. Multi-tenancy in Kubernetes goes beyond namespaces. Quotas and limit ranges keep one organization from consuming all CPU, memory, or storage. Network policies define who can talk to whom, limiting lateral movement and enforcing Fabric traffic patterns. From there, choose the tenancy model deliberately. Shared clusters reduce cost, consortium clusters balance governance, and organization-owned clusters maximize isolation. When regulatory or trust boundaries are strict, Separate clusters, private networking, and independent administration are usually worth the added complexity. Fabric components depend on identity material, MSP folders, TLS certificates, CA credentials, and admin keys. In Kubernetes, these are often packaged as secrets and mounted into peer, orderer, or CA pods at the exact paths Fabric expects, such as MSP and TLS directories. But secrets are not a vault by themselves. Encrypt them at rest, restrict access with RBAC, audit usage, and never commit private keys or enrollment secrets to manifests or repositories. For production, don't treat Fabric keys and certificates as ordinary Kubernetes YAML. Keep the source of truth in Vault, a cloud secret manager, or an HSM-backed system. Then synchronize only what workloads need without storing values in Git. Rotation should follow a controlled sequence. Issue or renew, sync the secret, update mounts, reload the component, validate peer, orderer, and client connectivity, then revoke the old credential. Test this path first, with rollback ownership clearly documented. Raw Kubernetes YAML is useful because it shows exactly what will be deployed, but it becomes fragile when each environment needs small differences. Helm packages Fabric deployment logic into charts, with values files for ports, images, storage, and domain names. CouchDB takes another approach by layering environment-specific overlays on top of a base. Keep these artifacts in version control, so releases are reviewable, repeatable, auditable, and easier to roll back. Operators and GitOps move Fabric operations from manual runbooks to declarative control. An operator captures Fabric-specific knowledge in custom resources, then reconciles peers, orderers, CAs, upgrades, configuration, and certificates automatically. GitOps adds a governed source of truth. Changes are proposed in Git, validated, approved, and continuously applied to Kubernetes. Together, this pattern supports promotion across dev, test, staging, and production, with audit history, policy checks, and drift detection built into the workflow. The main takeaway is that Kubernetes is more than a place to run Fabric containers. Production readiness comes from the full architecture: workloads, storage, namespaces, policies, secrets, certificates, automation, monitoring, and recovery. Next, we build on this foundation with multi-cloud, CI/CD, security hardening, scaling, observability, backup, and disaster recovery.